Okay, everybody. Here's 2.5 after the quiz about the inverse of quadratics. So we've seen some inverse stuff before. This is just going to be in terms of quadratics, so it's kind of pared down a little bit easier and very specific to quadratics. There's one new thing about restricting the domain to make it work, but other than that, it should be pretty familiar. Okay, so yeah, remember this stuff about inverses from kind of 2 units ago. Function and its inverse are mirror images over this line. It's a reflection over the line y equals x. One way to find inverses is to switch x and y in the equation and solve for y. We've also done this before, verifying inverses by doing f of g of x and g of f of x. And yeah, think about this. How is the original function's domain and range compared to the domain and range of the inverse? They, like everything else you might imagine, they actually switch places. So the domain of the original function turns out to be the range of the inverse, and the range of the original function turns out to be the domain of the inverse. All right, so consider this function negative 2x plus 1. Sketch a graph. I don't know why you don't get graph paper. The key version I'm looking at, they gave graph paper, so there's some space over here. So negative 2x plus 1, this goes through the graph, or through the y-axis at 1, has a slope of negative 2, so it's kind of steeply down, kind of like this. I'll graph this one in red. And then let's talk about, well, so yeah, this would be like 1, negative 1. It's going to go down there, and it's going to have this slope of 2. So every time you go over 1, you go down 2 and that kind of thing. Sketch a graph of the inverse. Okay, I'm going to change color. The inverse is going to be reflected over this line here. This is the y equals x line. The inverse on the same grid, I'll leave the same color. Instead of the x-intercept, or sorry, the y-intercept being here at 1, I'm actually going to think about the intercept now being there. I'm going to reflect that point. This point that's at 1, negative 1, is it going to end up going over here? The slope, it's almost like if I just turn my head sideways, this slope is going to go, like this is going to go down 2, kind of an up 1 like that. I'm going to get this line that looks something like this. It should cross itself on the reflection line there. It's going to look something like this. No, I did that. I did x as y as a dotted purple thing, and then, yeah. Algebraically find the inverse. All right, I'll go back to my answer key color. To find the inverse of this, we're going to do the switcheroo like they talked about at the beginning. We're going to switch x and y, so now x equals negative 2y plus 1, and then we just solve this for y. X minus 1 equals negative 2y, y equals x minus 1 over negative 2, but if you want this in slope-intercept form, you could do this as negative 1/2 x. What would that be? Plus half. Yeah, and that should be the equation. Maybe I should have stayed in purple. That'll be the equation of the purple line. Up there, yeah, that intercept looked like it might be at half. The slope is definitely negative. It's negative 1/2, which is easier to see if you have actual graph paper. So yeah, there's a relationship between those two lines. They're not, I don't know, they're not, maybe it's not as obvious as you might have guessed. Maybe you couldn't have guessed that that was the inverse. But yeah, they have this relationship that you're supposed to notice here, that they are reflections over this line here. Okay, next warm-up. Sketch the inverse of this graph. Well, if we're supposed to reflect everything on this line, then the reflection, we can just kind of reflect one point at a time like you used to do in geometry. This point's going to be the same. This point's going to be the same. This point over here at negative 1, that's going to reflect over to there. This point up here, because I don't think you can see where I'm pointing, is going to go to there, and this point over here ends up like that. So this whole thing, this is going to curve this way around that reflection line, and we're going to get a parabola that looks something like that. That's the reflection of the original parabola. Is the inverse a function? No. It does not pass the horizontal line test, or sorry, the vertical line test. It's not a function. I've got, yeah, 2 values. You can see right here, I've got 2 values of the function that have the same x value. That's not good. So it's not a function. So algebraically find the equation of the inverse. Well, that would be done by doing y equals x squared. That's the original. I'm going to switch x and y. X squared equals, sorry, I'm going to switch x and y. X equals y squared. Solve this for y. Well, technically speaking, if I'm taking the square root on both sides, I got to do that. And this isn't really a function, right? Like this tells me right now I've got 2 x values that produce the same y. So that's not really a function, right? That's exactly this sort of problem I was having here, where I had 2 values and the function that had the same x and 2 different y's. So yeah, it's not a function. So let's go on. Restricting the domain. So this would work. It'd be really nice to be able to do inverse stuff, or we could you know talk about a little bit having an inverse if we just do this. Restrict the domain. So we only consider a portion of the parabola. So they took this original parabola and they cut it in half, and they cut it in half 2 ways. This one, they restricted the domain to just be, and I'm going to do this in interval notation, from 0 to infinity. And here, well, can I make this, can I, really? Okay. They restricted, I have better handwriting, I feel like. Restricted domain here is from negative infinity up to 0. And once you do that, then you try to do an inverse. Like, what happens if we reflect this? I like using this purple for some reason. If we use this as, the reflecting line, or we use this as the reflecting line, this function over here turns into, I still have that, I still have that. This point goes here. I just have this curve right there. That's all there is to it. That's a complete reflection of that whole thing. This one, I have the same point there, and then I go probably here, and I get this kind of thing. That's, each one of those things separately is a function. Like the inverse of x so far is a function. Now, if this is f of x, this other thing is f inverse of x. It's a function if f of x is only what I saw here in the first place. So restricting the domain is a way to kind of take a function that was not going to have an inverse and restrict it to a partial function that does have an inverse that can be used for something useful. Okay, so what are you going to have to do? Take this thing and restrict its domain. So the original, let's talk about the original graph. This was going to be a parabola in vertex form, right? So the vertex here is at -3. It has an a of 1, so it would go over 1, up 1. It would go over 1, up 4. Notice I'm only doing one of these because it said the first thing it says to do is restrict the domain. So I'm only going to graph half a parabola. Like we saw up here, half a parabola is going to be invertible. So that's kind of what I want to do. How much of it did I graph? Well, I graphed the part that was over the domain from -3 to infinity. Now I could have also done like the negative half, kind of like that. But I'm an optimist. I like doing the positive side. I'll just say this. I chose the positive side. You could have chose the negative side. That would also work. It's just then your inverse is going to look different than everybody, the positive people. It's totally fine. I don't have any reason to select one over the other. So I graphed the restricted domain. Now graph inverse of x. Inverse of x is still going to be reflected over this line like this. So I'll keep purple for the inverse. Purple for the inverse is going to go, so it's almost like I'm just turning my head sideways. I'm going to have a parabola where that's the vertex, and it's going to curl around kind of this way. And it's just going to feel like that. And that's what it looks like. Algebraically determine this thing. I will stay purple. Y plus 3. I'm taking the original thing and just switching things around. Let's take the plus or minus square root of x equals y plus 3. Now, wait a second. I took plus or minus square root, but that's not a function. But I really only care about half of this, right? I care about either the plus or the minus to make this happen. Well, since I took the positive side up here, I'm only going to care about the positive version of this. So because of the restriction, this really turns out to just be then -3 plus the square root of x. It's not plus or minus because we know from before that's not a function. Just so you know, in the calculator and just kind of by definition of the notation, when we write radical in front of something, we are kind of by convention taking only the positive version of that. So yeah, so by itself, this thing means the positive square root. It's not. That's why we have to say plus and minus in front of it. It's not like it's this every solution to something like y equals back to here, back to this. If x equals y squared, the solution isn't simply radical x equals y, because radical x is defined to be positive. There's more than just that one solution to this. There's actually two solutions. You could have a positive or a negative version of that square root. So yeah, but by itself, if you don't see that symbol in front of it, it is defined to be the positive one, which is kind of convenient, actually. All right, let's do this again. We have a function where we have 2 times x minus 4 squared minus 1. This is vertex form already, so let's just do vertex form. That's, whoops, that's not where it goes. It's -4, comma, the vertex here is, I remember how to do this. 4, negative 1. So it's over here. What was I doing? 4, negative 1's right there. And then it has an a of 2. Let's do the positive side again. Again, I'm just I'm an optimist, so I'm just going to do the positive side. I'm going to do the... You could do the negative side if you're feeling pessimistic. That's totally fine. Up 1 over, sorry, over 1 up 2, up over 2 up 8, 2, 4, 6, 8. It's about there. I'm graphing just the positive side of this parabola. I'm going to purple flip it across this, this line. So that point's going to be right there. This 4, negative 1 is like 4, negative 1 there. And then 5, 1, it's kind of here. And this is the half parabola I get there. Yeah. And so, oh, actually, I'm going to stay purple, aren't I? That would be more fun. Now we're talking about x equals 2y minus 4 squared minus 1. X plus 1 divided by 2 equals y minus 4 squared. And we know we're taking just the positive version of this. So I'm just going to say positive. X plus 1 over 2 equals y minus 4. So the final answer is 4 plus this big nasty square root, x plus 1 over 2. And you don't really have to simplify it any farther than that. Okay, then we have example 3. That's interesting. Okay, sorry, I'm looking at something else. Determine the equation for the inverse. Well, an equation for the inverse, we kind of have to, let's just kind of restrict the domain first. Restricted domain should be from, because you usually have to say this off to the side, like this inverse I'm about to write is under the assumption that we're only talking about numbers in the restricted domain of the original f of x to be this. Okay, then I'm going to reflect it over this line. Oh, it doesn't say determine, well, yeah, I'll make a graph. This thing's going to reflect here, 2, 3, 2, 3, that's going to go there. Vertex is at 3, 5. 3, 5, it's kind of there. And it's going to be a parabola that kind of goes this way. But if I'm supposed to determine this equation, it's kind of hard to determine the equation from that. I'm going to determine the original equation from this kind of stuff. The vertex was here at negative 3, 5. What's the a? Well, the a, we've done this a lot. The a, I go over 1 down 2, over 2 down 8. This is going to be negative 2. So f of x is negative 2 x plus 3 squared plus 5. Determine the inverse. We're going to get x equals negative 2y plus 3 squared plus 5. X minus 5 divided by negative 2 equals y plus 3 squared. Take the square root. Oh, I'll do it this way. I was going to use my eraser and be all fancy. All right, negative 3 minus this big, huge, plus this big, huge square root, negative 5. You might be looking at this going, wow, that's a lot of negatives under that square root. Well, we don't know anything really about x, the nature of x. I know this is actually going to work. If you try any of these numbers that work for the, this would be easier, in this, like, domain of this, this thing I've already graphed, you'll notice most of them are kind of negative. But as long as this is 5 or bigger, like this should be okay. Or sorry, 5 or smaller, this should be okay. I'll have a negative on top divided by negative gives me a positive. I can take a square root, so it still works. Okay, verifying inverses. So this we started doing this in the log chapter or log unit. It's just, yeah, f of g of x and g of x have to both be x. So they're going to give you some stuff and you have to give you some functions and you have to figure out if it's inverses by doing it that way. This does not mean, or if these are the instructions, it's not okay to take this one, switch x and y, solve for y, and see if it turns out to be this. That's not what's intended here. You have to actually plug them into each other. So f of g of x here is the f kind of structure, but I'm going to plug g into it. So it's a square root of 2x squared minus 1